Hi, welcome to my PyOhio 2023 talk. I'm going to talk to you about digital signal processing and why you should be doing it in Python as an alternative to the very classic approaches and methods in MATLAB. My name is Meg, and I have a background in biomedical electrical engineering. I've worked in the medical hardware industry, specifically looking at a lot of biosignals and processing them, digitizing them from analog, and making them ready for machine learning use cases. Currently, I work as a research engineer at the Cleveland Clinic, where I also espouse the importance of using Python, oftentimes as an alternative to R. So I'm a big fan of Python, and I think the digital signal processing world can definitely make use of some of the functionalities that have come up in Python and its associated libraries, something I'm going to talk about today. So what exactly is digital signal processing? Digital signals are commonplace. We see them everywhere in our modern world. Some examples include biosignals, and this is really tied to medical applications, such as an ECG or electrocardiogram waveform shown here. We have electrical activity of the heart that can be measured. There's also signals like electroencephalogram that track brain activity, as well as electromyography, which looks at electrical activity of muscles. So there's different ways of studying human physiology and function through the signals that are acquired. And these, in these particular cases, are analog signals that are sampled and then turned into a digital waveform for us to then study. There are a lot of other signals, though, that cross domains, such beyond the medical domain, such as mine, such as audio signals. And you guys might be familiar with this when you listen to headphones, and they're tuned and they're filtered for different frequency responses. And so this is a very interesting field with a lot of signal processing work being done in the digital realm. Typically, MATLAB tends to be, the electrical engineer's mainstay in this space. There are a lot of specialized toolboxes for filter design, as you can see here, just for visualizing the signal, looking at the different kinds of amplitude changes and frequency responses. We can also perform a lot of signal analysis, and there is some availability of machine learning plugins to also do predictive work. However, I'm in this talk making the argument that Python is really a fantastic alternative. And number one, I'd say it's open source. MATLAB is costly. It also requires installations of separate toolkits, such as the digital processing toolkit, to get your work up and running. And that's not the case in Python. In Python, it's a very simple pip install, which really makes that addition of a new type of analysis you want to do very seamless. It's also the lingua franca of data science, and as our analyses and development of tools and hardware technologies become more data-driven, I think it's very important to keep up with the language most engineers are using. And there are so many fantastic libraries like matplotlib and seaborn for visualization, numpy, scipy, pandas, data frames that have become the norm for the kinds of processing tasks that involve digital signals. The other thing I really like about Python is that it's also ID agnostic, and if you're familiar with MATLAB, that ID, it's not the best, and I think it's a lot easier to also deploy easily in a web app, and much more seamless integration with the kinds of predictive machine learning applications in PyTorch and TensorFlow. So now that I've hopefully made an argument that there are a lot of good things about Python, let's walk through an example of what does digital signal processing look like. So here's an ECG waveform, a raw ECG waveform, so it has not been processed. And what we often see in this kind of waveform is that there are noise sources. So the signal is not as clean because it's picking up during the signal acquisition process sources of noise that could be motion artifact or a power line interference. And we really want to clean that up before we start extracting interesting information from our waveform. But there is a lot of interesting stuff that we can extract and then, feed into ML downstream to classify it. And Here's an example of a lot of the features that can be extracted that are of physiological meaning and importance. So the waveform tends to be broken down into these waves, the P, Q, R, S, T, and we can extract things like the QRS complex or the RR interval between ECG signals. And this is very interesting because there's a lot of tooling that allows us to even find, well, where is that peak of the R wave? And in scipy, there is a function very synonymous with the MATLAB one called find peaks. In scipy.signal.find peaks that allows us to pinpoint that peak of the R waveform. We can also perform filtering, and here you can see the ECG waveform. Originally the raw waveform is in blue, and then the filtered processed waveform is in orange. And we can remove and smooth out some of those noise sources and end up with a better signal that's easier to work with for any kind of downstream analysis we want to do. An example of a library that is very, very useful for this kind of work is PyWT. It's the wavelet transform library, which actually applies time frequency transforms. So it doesn't just look at the time domain or the frequency domain of the signal, but actually processes it in tandem. It's very, very good for addressing the kinds of noise we see in biosignals that happen during the acquisition process. And that's what we've done here. So I'm going to walk you through just one example of the kind of filtering that's available here in this open source library. So for wavelet filtering, we'll really just start with a very quick pip install of the package of interest and perform a decomposition of that ECG signal to get its coefficients. And this is a very traditional step, if you're not from the signal processing world, to do the processing on the decomposed coefficients. So wavedec is that method that allows us to do that. Moving forward, we then set a threshold, as it typically is done for filtering, and apply that threshold to our coefficients. And here's where reading the documentation of PyWT can be really helpful if you want to make modifications on how it's applying that threshold. So I also really recommend going to the Library of Interest's website and reading more about it if the default settings of or configurations of that method are not giving you the results you want. And I think plotting it out using Seaborn or Matplotlib is a really good way to see what's happening to your signal. Next, we then reconstruct the signal. So waverec allows us to quickly, very cleanly reconstruct and get our original waveform. And that is what you see here in orange. So beyond things like filtering, there's so much more we can do in Python that are really correlated to the kinds of functionality we see in MATLAB. One is the fast Fourier transform, and I think this is a very classic type of application that I use all the time. And that's actually in scipy itself, so you don't have to go into another library. You can import FFT to do the fast Fourier transform and IFFT for the inverse. We can also do Bode plots, and this is really fantastic if you're playing around with the transfer function itself. I've plotted a really basic one here, but you can examine it both the magnitude and the phase using like a one line to pull out the magnitude and phase components. And this is just so fast, so intuitive, and very similar to how you do it in MATLAB. Another thing we can do is design the filters ourselves using the signal toolkit. And here I've shown a Chebyshev 1 filter with a few parameters shown here. And it's very easy to quickly plot that, see how it's looking in Matplotlib without having to tinker around with the filter designer like you kind of have to do in MATLAB. So in summary, the classic signal processing methods are available in Python just as they are in MATLAB. MATLAB was built before Python, so the designers of scipy and all these other toolings have taken the nomenclature of MATLAB. So it's a very easy switch from MATLAB to Python. It's open source, which makes it so much more economical, and it's very, very well maintained. So you're not worried about becoming out of date and using an older version of the software. So I really think there's a lot of positive benefits of making the switch from MATLAB to Python for your digital signal processing work. And if you're new to the signal processing field, there are a lot of fantastic and very easy to learn ways of processing signal for your other types of use cases, such as data science or machine learning applications. So thank you very much for listening, and please do follow me on Medium, where I enjoy writing about these kinds of topics, and connect with me on LinkedIn. Thank you very much.